Assalamu alaikum. I am Sabil Shameen, student of BS Mathematics. This is the course of functional analysis. The topic of the lecture is open mapping theorem, which is one of the most important theorem in functional analysis after the Hahn-Banach theorem and uniform boundedness theorem. The outlines of the lecture include the definition of open mapping, and then we will state and prove open unit ball lemma, which is then used to prove this important theorem, the open mapping theorem. In the meanwhile, we will also discuss some concepts which is used to prove open unit ball lemma. So first of all, recall an open set because this will appear again and again in our lecture. So recall it that a subset M of a metric space X is open if it contains a ball about each of its points. If we take a point X from M, then we can find a ball of radius r centered at that point, and the ball is contained in the set. And this happens for every point of X. If we take any X from the set M, we can find a ball of radius r and centered at that point X. That is the ball is contained in M. The ball is the subset of M. This happens for every point of X, then M is an open set. Open mapping. An open mapping is a mapping which maps open sets to open sets. If we take an open set in the domain of T, then the image of that set will be open in the range of T. If U is open in the D of T, then the image of this open set T of U will also be open in Y. So here's the definition that let X and Y be metric spaces we call T from D of T to Y with domain D of T subset of X an open mapping if for every open set in D of T the image is an open set in Y. Here is a remark that do not confuse this with continuity. We have studied a definition of continuity which says that T is continuous if and only if the inverse image of any open set in the range of T is open in the domain of T X. But this is a different thing. An open mapping is a mapping which maps the open set from the domain to the open set in the range. But continuity is different. Here we take an open set in the range of T, and the inverse image of that open set is open in domain of T. A continuous mapping is not open in general, as this example suggests. This is an example from R to R, and this maps 0 2 pi an open set to minus 1 1 closed interval, that is a closed set. And this is an easy example which shows that a continuous mapping is not open in general. Here are some properties of open balls. Recall that an open ball centered at x0 and of radius r is the set of all those points which have the distance less than r from the center x0. If we have a ball of radius r centered at 0, then this is same as r into the ball of radius 1 centered at 0. So I have named it b dot 1 so that when we used it in our proof, you should recall it. Here is another property of an open ball, that if we have a ball of radius r centered at 0 and we translate it by x, then we will get another ball of radius r, the same radius, but in this time the ball will center at x. This is another property b dot 2. Remember these two properties. Bayes' principle or Bayes' category theorem. This is also used in the proof of open unit ball lemma, so you should remember it when we use it. It says that if X is a complete metric space and it is equal to the countable union of closed sets. These AKs are closed. All AKs are closed. If X is complete metric space and it is equal to the countable union of the closed sets, then the Bayes principle claims that there will exist at least one of closed sets which will contain a non-empty open subset. At least one of these closed set will contain a non-empty open set and consequently open balls. Now we come to our main topic, the open unit ball lemma. This is the lemma about the image of an open ball. It states that if we have two Banach spaces X and Y, so X and Y are Banach spaces, and T is the linear operator from X to Y. If we take an open unit ball in the domain X, B0 is an open unit ball centered at 0. It is of radius 1, so it is called a unit ball. So if we take an open unit ball in X, B0, and then the image of this ball, T of B0, will contain a ball which will centered at 0 of any radius r, but it will be centered at 0. The T of B0, the image of an open unit ball, will contain another ball which will be centered at 0. So here is a statement that is a bounded linear operator T from a Banach space X onto a Banach space Y has the property that the image T of B0 of the unit ball B0 contains an open ball about 0 belongs to Y. If T is bounded linear operator and it is from Banach space X onto a Banach space Y, onto means it is also surjective, then the image of the open unit ball B0, which is of radius 1 and centered at 0, the image of this ball T of B0 will contain a ball which will be centered at 0. This is the statement and this is the thing we want to prove. The proof here is divided into 3 steps. The first step is that we will take a ball of radius 1 by 2 centered at 0, call it B1 in the X, and we will prove that the closure of the image of this ball, closure of T of B1, contains an open ball B star. This is our first step. The second step is that we will prove that closure of T of Bn, where Bn is the set of open balls of radius 2 power minus n, will prove that the closure of image of these open balls contain a ball Vn about 0. And in the third step we will prove what we want to prove, that the image of the B0 contains an open ball about 0 belongs to Y. So these are the steps, this is the process we will do. So let's start the step 1. Consider the open ball B1 of radius half centered at 0 in X. Then any X belongs to X is in KB1, because if B1 is the ball of radius half, then KB1 is the ball of radius K by 2. Here we use B dot 1. Now if we take K sufficiently large, that is greater than the norm, double of the norm of X, then we will get a ball of radius greater than norm of X, and consequently it will contain X. Hence, and this is can be done for every X belongs to X. Hence the whole space X is equal to the countable union of these balls KB1. Now since T is surjective, we can write Y as the image of whole space X, because T is surjective. Instead of x we have write this because x is equal to this. And now t is also linear, so t of k of b1 is equal to the countable union of k t of b1 because t is linear. And here we have replaced into t of b1 with the closure of this, because this makes no difference, because this is already equal to the whole space y, and by adding closure we haven't make any change, there is no difference here. Now since it is given that y is a Banach space, so it is complete, and it is also the countable union of the closed sets, that is the closure of the k t of b1. So we can use here the Bare's category theorem, which we stated earlier, that one of these closed set will contain an open set, and consequently it will contain open balls. So if k of t of b1, closure of k t of b1 contains open balls, so the closure of t of b1 will also contain open balls. And say it contains an open ball b steric, which is equal to the, let's say it is centered at y0 and of radius epsilon. So this ball will be contained in the closure of t of b1. So this is what we wanted to prove in the step 1. And now as the ball at the centered at y0 and of radius epsilon can be written as y0 plus the ball centered at 0. And this is by b dot 2, the translational property of open balls. It follows that b steric minus y0 is equal to the ball centered at 0 and of radius epsilon. Then, and it is contained, as the ball b steric is contained in the closure of the t of b1, so b steric minus y0 is contained in the closure of t of b1 minus y0. Now we go to the second step. We prove that b steric minus y0 is contained in the closure of t of b0, where b0 is the ball of radius 1 centered at 0, which was given in the statement. Now as we have proved that b steric minus y0 is contained in the closure of t of b1 minus y0, now we will prove that it is also contained in the closure of t of b0. So how we will do this? We will prove that this t of b1 minus y0, this is contained in the closure of t of b0, and it will automatically prove this. So let we take an element y from the closure of t of b1 minus y0. Then y plus y0 belongs to the closure of t of b1. And we remember that y0 belongs to the closure of t of b1 because y0 is the center of the ball which was contained in the closure of t of b1. So y0 belongs to the closure of t of b1, and hence we have 2 points in the closure of t of b1. And here is the theorem which states that if an element belongs to the closure of a set, then there must be a sequence in that set which approaches to that point. So here we have 2 points y plus y0 and y0 which are in the closure of a set T of b1. So we can find 2 sequences, namely un and vn, such that un approaches to y plus y0 1 point, and the vn approaches to y0 the other point, and un is equal to t of wn, where wn is a sequence in b1, and un is equal to t of zn, where zn is also a sequence in b1. Now since I said that wn and zn are the sequences in b1, and b1 was the open ball which has the radius half, so it follows that the norm of wn minus zn is less than or equal to the norm of their sum, because according to the triangle inequality, and as the norm of wn will be less than 1 over 2 because it is contained in the ball of radius 1 over 2, and zn is also in the b1, so its norm will also be less than 1 over 2, and the norm of Wn minus Zn will be less than 1. So Wn minus Zn is belongs to B naught. That is the ball of radius 1 centered at 0. Now T of Wn minus Zn is equal to Un minus Vn, and this approaches to y because Un was converging to y plus y naught, and this was converging to y naught. So y, the difference will converge to y, and hence the T of it contains in T of B naught, there is a sequence in T of B naught which converges to y, so y will belong to the closure of T of B naught. Now since we have taken y from the T of B naught, closure of T of B1 minus y naught, it was an arbitrary element, so, and we proved that it is contained in the closure of T of B naught. So T of B1 minus y naught is contained in T of B naught, closure of T of B naught. So thus B steric minus y naught, which was equal to a ball of radius epsilon centered at 0, this is contained in the closure of T of B naught. Now let Bn is the set of open balls centered at 0 and of radius 1 over 2 power n from X. We can write Bn also in this form because by using B dot 2, where B naught is equal to the ball of radius 1. Now since T is linear, we can do this, that T of Bn is equal to 2 power minus n T of B naught, and by taking closure it is also equal to, and now by taking closure it is also equal to this, that the closure of T of Bn is equal to 2 power minus n the closure of T of B naught. Now so Vn will be, is if we take Vn equal to the balls, set of balls of radius epsilon by 2n, then this will be contained in the closure of T of Bn. Now we prove that in the step 3 we proved that what we wanted to prove. What is the aim of this lemma? That an open ball centered at 0 is contained in the image of the open ball, unit ball. And we will do this by showing that if we take an arbitrary element from V1, that's from this ball, it will be in T of B naught. So let y belongs to V1. Now as y is from V1, it has radius epsilon by 2, and if we put here n is equal to 1, that then it will be contained in the closure of T of B1. So here it is written that V1 is contained in the closure of T of B1, hence y is also in the closure of T of B1 because we have taken y from the V1. Now y belongs to the closure of a set, so there will be a sequence approaching to y. It means that there are elements in the set T of B1 such that the distance of the V from the y is as less as we want. V is as close to y as we want. So the difference y minus V norm will less than equal to some epsilon by 4. Now V belongs to T of B1, so this implies that V is equal to T of x1 for some x1 belongs to V1. So we can write y minus Tx1 norm is less than epsilon by 4. Now V2, if we put 2, then we will get a ball of radius epsilon by 4, and the norm of y minus Tx1 is less than epsilon by 4. So it is less than epsilon by 4, so we can say that y minus Tx1 is belong to V2. As before, we conclude that there is an x2 belongs to B2 such that this is equal to T of x2. So y minus T of x1 minus T of x2, as before we conclude that this will also be as close as we want, so epsilon by 8. Hence y minus T of x1 minus T of x2 belongs to V3 in the same way as we previously show. So this belongs to the closure of T of B3 and so on. And in the nth step we can choose and xn belongs to Bn such that the norm of y minus t of xk's, where k varies from 1 up to n, this will less than epsilon by 2n plus 1. So the 2n plus 1 appears from here, 4, 8, 12, and so on. Now we suppose that a sequence Zn is equal to x1 plus up to xn. Since xk belongs to bk, x1 was belonging to b1, x2 to b2, x3 to b3, and so in general xk is belongs to bk. So we have the norm of xk less than 1 over 2k, because b1 is the ball of radius half, b2 is the ball of 1 by 4, b3 is the ball of 1 by 8 in this. So xk, the norm of xk will be less than 1 over 2 power k. So if n is greater than m, the difference between the Zn minus Zm and its norm will be less than or equal to, this is by triangle inequality, the norm of xk. K is from m plus 1 up to n, because before m all the terms cancel out and we get only k plus terms from k m plus 1 up to n, and this is less than 1 over 2 power k by this inequality, and this approaches to 0 as m approaches infinity. So hence Zn is Cauchy, because the difference between the terms is getting smaller as m is getting larger. So Zn converges, and it will converge to a point of x, because x is a Banach space, and also x belongs to B0, because as k approaches from 1 approaches to infinity, the sum of the norm of xk's, which is 1 over 2k, this is a geometric series, is equal to 1. B0 is the ball of radius 1, and the norm of xk as k approaches to infinity is also less than 1. So x, the limit of the Zn, also belongs to the ball of radius B0, ball of the radius 1. Since t is continuous, and because it was given that t is bounded and bounded linear operator is also continuous, and Zn approach to x, so the continuity of t implies that t of Zn will approach to t of x, and 5 shows that t of x is equal to y, because the norm of y minus t of Zn was less than an epsilon, and t of Zn approaches to t of x, so the norm of y minus t of x is less than any epsilon. So this shows that t of x is equal to y, and as x was belonging to b0, so y belongs to t of b0, because it is equal to the t of x where x belongs to b0. We take an arbitrary element from a ball centered at 0, and which implied that y belongs to the t of b0. Hence, the ball centered at 0 is contained in the image of B0, and this was what we wanted to prove, that the image of an open ball under bounded linear operator, which is this, contains an open ball centered at 0. This completes the proof. Now we come to the theorem, open mapping theorem. This theorem is about the conditions under which a linear operator becomes an open mapping. So these conditions are that a bounded linear operator T from a Banach space X onto a Banach space Y is an open mapping. So first is that the operator is bounded and it is surjective. It is from Banach space X onto a Banach space Y. Then this T is an open mapping. We prove that for every open set A subset of X, the image T of A is open in Y. So this is what an open mapping means, that we will take an open set from the domain and prove that the image of this open set is open in Y. And we will prove T of A is open by showing that any arbitrary element in the T of A, for any arbitrary element in the T of A, there is an open ball which is contained in the set T of A. This is the definition of an open set. So suppose that y belongs to T of A, and so it will be equal to some T of x. Now since A is open, because we suppose that A is open and wanting to show that T of A is open, so since A is open, it will contain an open ball centered at that point x. So x belongs to this ball which is contained in A. Now we can write this as x plus the ball of radius r centered at 0 by using b dot 2, which is the translation property, and from this we can write this, that ball of radius r centered at 0 is contained in the set A minus x. So A minus x contained in a ball with center 0 and radius some positive r. Now from 1 we can write this as the r into the ball of radius 1, because we can use here b dot 1, the other property of open ball, and from this expression im- implies this expression that the ball of radius 1 centered at 0 is contained in the set k into A minus x, where k is 1 over r. Hence k into A minus x contains an open unit ball of radius 1. So open unit ball lemma, we will use here open unit ball lemma. So open unit ball lemma implies that the image of this set under this linear operator will contain a ball about 0. This is from open unit ball lemma, which we just proved. So T of A minus T of X will also contain a ball about 0, safe of radius S. So T of A minus T of X contains a ball of radius S centered at 0. So we can use here B dot the translation property of open balls. T of X is equal to Y, and Y plus this is contained in T of A, and so we can write it by the translation property of the open ball that Y plus B ball of the radius S centered at 0 is equal to the ball centered at Y and of the same radius. This is contained in T of A. Hence T of A contains an open ball about Y. Now we have taken an arbitrary element from T of A and proved that this T of A contains an open ball about this arbitrary point. So T of A is open. So for as A was open, the image of A is also open. So T is an open mapping, which the open mapping theorem claims. Here is a corollary which directly follows from open mapping theorem. It is known as bounded inverse theorem. It states that if T is a linear operator from a Banach space X to a Banach space Y, and if it is continuous and it is bijective, then T inverse is continuous. So bijection guarantees that T inverse exists, and if T inverse exists, then by open mapping theorem it is continuous, because we have stated a definition of continuity earlier, that if the inverse image of every open set is open, then the linear operator is continuous. So the domain of T inverse is Y and the range of T inverse is X. So if T is open, then T inverse is continuous, because if we take any open set from the range of T inverse X, it will be open in the domain of T inverse X. So by definition of continuity, it is continuous. And why will every open set from X continuous in Y? Because T is an open mapping, and by open mapping theorem. So this is the bounded inverse theorem. Thank you very much.